Good morning, boys and girls, and welcome back. Here's where we finally get to the good stuff of calculus, the fundamental theorem of calculus. And it's so good, we're even going to start with the second part of the fundamental theorem of calculus. Now, when I think about it, though, I really think about this as the first part of fundamental theorem, because it's the part we probably use most often. But I think because it stems from the part I'm going to show you tomorrow, the first part, we call this the second part of the fundamental theorem of calculus. But I'm already getting ahead of myself, right? Let's first start today talking about what an area function is. Yesterday, we were talking about a definite integral and how a definite integral is the area under the curve, right? When I have a definite integral from one limit to the next limit, that is going to give me the area under the curve. And I can turn this into an area function by saying that, hey, the function under my curve, the area under the curve for any value x, is going to start at a and go to some value x of the function, whatever we're dealing with. The only kind of tricky part of this when we start turning our integrals into functions is you now need like two variables. I need one variable in terms of x for my function, and then like this kind of dummy variable, and we generally use t, since I can't use f of x inside my thing anymore, since x stands for the the input of the main function, of the area function. Okay? Oh, and I wrote t here, where x is greater than or equal to a. Geez, see? Already getting my variables all mixed up. And this is going to be true anytime, so long as x is greater than or equal to a. This would be the area of our graph. All right? Let me show you a quick example of this. Okay, so here is our area function. A of x is the integral from -1 to x of f of t dt. And we're given a graph of f of t right here. And so we're going to first try to find, hey, I want you to go find a of 3. So that would mean that, hey, I'm going to try to find -1 to 3 of f of t dt. And so again, what we mean by this is the area function. Now this is just the area under the curve from -1 to 3. And so now kind of using what we talked about yesterday, since that is the area underneath the x-axis, we would say that this is a -27. Okay? Do another one just real fast here. If I found a of 5 instead. If I do a of 5, this is the integral now from -1 to 5. Again, when we do like a of 5, we're just plugging in for x, right? So I'm just plugging in for this x value in the integral now of f of t dt. So now this just represents the area, the net area under the curve from -1 to 5. So from -1 to 3, we said we had -27. And then from 3 to 5, we have a +3. So the net area would be -24. So that's kind of how an area function works. Now we can use this idea of an area function to help prove the second part of the fundamental theorem of calculus. Okay, so there's a great derivation of the fundamental theorem of calculus in your books. If you want to go look at, before you do all the problems, you can go look at it. It's awesome. It's very informational, but I don't have the time to go through it with you right here. But if you want to go look at that, go and take a peek of it. But here's what we've all been waiting for. I'm so excited I can't even talk. The fundamental theorem of calculus. Okay, if we want to evaluate the integral from a to b of f of x dx, and I want to do it algebraically as opposed to geometrically like we did yesterday, what we're going to do is this integral is equal to the, remember capital F is the antiderivative of little f. So this is equal to f of b, big F of b, minus big F of a. That is the second part of the fundamental theorem of calculus. It is saying that what we can do is we can take the antiderivative of our function, and then we're going to evaluate that from a to b. This is some common notation we use. And then what we can do is, that is then going to be equal to, like we said, f of b minus f of a. So I'll use some of this notation here in a second, but this means that we took the antiderivative of our integral, and now I want to evaluate it from a to b, and then, this is the fundamental theorem part, is I'm going to do f of the top number minus f of the bottom number, and that will give me the exact area under our curve. It is so cool. Now, you might not be all that thrilled with it, because I think a lot of you physics kids, geez, having troubles today, have been using this for a while, but one of the best things, fundamental theorem of calculus. All right, so I'm going to go back to our old and trusty, the integral from 0 to 2 of x squared dx. And now let's go and actually find the exact area under the curve, the exact value of this, using the fundamental theorem of calculus. Okay? So, we said what we first need to do, if I'm going to evaluate this integral, is I need to take the antiderivative. Alright? So the antiderivative of x squared, we add 1 to the exponent again, right? And then we divide by the new exponent, so it's x cubed over 3. And now I want to evaluate that, we say, from 0 to 2. There's so much going on here. What you want to do is really take one step, focus on finding the antiderivative, and then, do that. This tells me, this little line here tells me that you took the antiderivative of our function, and then now we're going to go and evaluate that from, 0 to 2. So, f of b minus f of a, or I get 8/3 minus 0, or this would be 8/3. And that is the exact area in the curve that we've been approximating with all our left Riemann sums and right Riemann sums and midpoint Riemann sums and trapezoidal approximations, and that is the exact value we've been trying to get. Now you might be asking me, hey, Mr. Mortara, I thought when we did the antiderivative of stuff, I thought you needed that whole plus c in there, right? Like, you harped on us. Whenever you take the antiderivative of something, you need a plus c. And I can say, yes, that is true on an indefinite integral, but you do not need it on a definite integral. If I put the plus c in here, and I had my x cubed over 3 plus c evaluate from 0 to 2, when I go to plug in, I would get 2 cubed over 3 plus c minus 0 cubed over 3 plus c. And you can see that when I distribute this negative, I get minus my 0 cubed over 3 minus c, that the c's are just going to cancel out with each other. So, when you do an indefinite integral without the limits, very important, you need the plus c. But if I'm doing a definite integral, when I'm evaluating it from a to b, then you can ignore the plus c and just use the antiderivative without the plus c. Alright? Let's do some of these now. Okay, so here's our next example, the integral from 0 to 2 of 3x squared plus 2x dx. Again, start of my integral, end of my integral, very important pieces of our thing here. And then I was thinking, as I was writing on this problem, I don't think on yesterday's video, we talked about this integral means antiderivative, right? And we said that was our antiderivative sign. However, I don't think I talked about, do you notice that this is kind of S-shaped? And again, what made me think about it was I didn't do a very good job of drawing my S shape here. But do you notice how this is kind of S-shaped or integral? And the reason for that is that integral also stands for the sum, right? We're finding the sum, S, sum, of all the areas of those rectangles. So again, a little more background information for you, kind of fun stuff. All right, but if I want to do this problem, again, what we're going to do is we are going to take the antiderivative of this function. So to take the antiderivative, we're going to do each piece individually. Again, you do the opposite of a derivative, so you're going to add 1 to the exponent, divide by the new exponent, plus add 1 to the new exponent, divide by the new exponent, and then we're going to evaluate that from 0 to 2. Again, worry just about taking your antiderivative. The more you get into this, the more you'll be able to take shortcuts. But in the beginning, I would write stuff out like this while you get used to it. Go back, when you're done, simplify now. This is just x cubed plus x squared. Go and take the derivative of this. Does that give me what we started with? Yes, that's 3x squared plus 2x, so I know I'm on the right path. But you really want to, take the time with this, show some work, make sure you don't mess yourself up because it is a little confusing in the beginning. Now, once you get here, you got to do your f of b minus f of a part. So I'm going to plug into 2 cubed plus 2 squared. That's my f of b. And I think it's important, again, especially in the beginning, make sure you're putting these things in parentheses. Not so much the first guy, and not so much on this problem, but on this second one, when we have to distribute this negative, or we have to subtract this thing here, I think you really want to make sure that you put your parentheses. I think it's a very good idea that you have your f of b minus f of a set up in parentheses is a good habit to do. In this case, now I'm going to get 8 plus 4 is 12, minus 0 plus 0 is 0, or 12 minus 0, or the answer to this would be 12. Okay, here's our next problem. The integral from 0 to ln of 8 of e to the x dx. Looks real kind of tricky and scary because now we're dealing with e's. Oh no! But again, just kind of go back and think about what we need to do. Okay, my first step is to take the antiderivative of this function. So the antiderivative of e to the x is e to the x. Take the derivative to make sure, hey, the derivative of e to the x is e to the x. So yay, that works out. I want to evaluate it from 0 to ln of 8. Again, this step, very important. A lot of times on an FRQ, you will get points for just having the antiderivative. So make sure you're setting up your step just like that. Don't rush into things. Okay? Now I got to do my f of b minus f of a stuff. So this is e to the ln of 8 minus e to the 0. Because I only have one term here, like we talked about in the last problem using parentheses, you could, but because I have just one term, I don't think I need to. And now, e to the ln of 8 would just be 8 minus e to the 0. Anything to the 0 is 1. So this is 8 minus 1, or 7, is my answer. Easy peasy lemon squeezy. Okay, now I want to go back to problem 2, and I want to show you how to do this stuff on your calculator. Okay? So now we're going to do the integral from 0 to 2 of 3x squared plus 2x dx on our calculator. Okay, so one way to do this would be to enter the 3x squared plus 2x, enter your function, into y1 on the calculator. If you want, you could then go and graph it. So there's our function. Okay? Now, to evaluate the integral, if you go to second, calc, if you go down to number 7, you'll see it has the integral symbol there. The integral of f of x. Now it'll ask you for the lower limit. You'll need to tell you we are going it from 0. Enter. It'll ask you for the upper limit. You'll say 2. Enter. And then it'll actually shade in the area under the curve. And it'll tell you, hey, the integral from 0 to 2 of f of x dx is 12. So one way to do this on your calculator is through the graphing function. Kind of like derivative. I don't use this very often from this, but it is kind of neat because it shades it in. More frequently, I do it from our main screen. Okay, back here on the home screen, again, to get to it, I'm going to go to math, just like we did for derivative. Derivative was number 8. Go down with me. Okay, derivative was number 8. Number 9, it says fn int. That is your integral, number 9. And if I hit 9, you'll see it brings an integral up. And now I would type this in exactly the way, the problem looks. 0 to 2 of... Now again, if you have it typed in, you could do alpha trace y1. Or you could type in your 3x squared plus 2x. And then again, just like we need to write, your calculator needs the differential. Okay? I'm going to take the derivative with respect to x. And again, this is normally the one I use. And again, you should get 12. It doesn't matter which way we do this. All the ways, anyways, there it is. Doing this again, doing problem number 3, we went from 0, to ln of 8. And our function was e to the x dx. And for that one, we got 7 and 7 our answer. So you can type those in either way, but I wanted to show that to you. On tonight's homework, this would be a great way to check your answers. You need to be doing the math algebraically tonight, right? But you could quickly double check your answers with your calculator. We need to know how to do both things. That's today's lesson though, boys and girls. I hope you enjoyed it, and I will see you again real soon.